Earth temperature is generally affected by 3 different cycles. The first cycle, the daily cycle, is what we experience when we go from nighttime into daytime. As we traverse that cycle, when we get into the daytime, temperatures tend to be warmer than at night. As we move into night and approach midnight, temperatures will tend to be cooler than in the day. And this cycle tends to repeat itself every day regardless of the time of the year. Essentially, we'll experience one of these cycles every 24 hours. The next cycle that tends to affect the temperature of Earth is the yearly cycle. Basically, as we move from winter into summer, summers tend to be hotter than winter, and winters tend to be colder than summers. And this will happen throughout every year that we experience. I'll point out that the daily cycle that we saw previously is constantly occurring. There's little ups and downs on this annual curve here, and that happens 365 times every year. This yearly cycle is essentially controlled by the tilt of Earth's axis. When the northern hemisphere axis is tilted more towards the sun, that will bring summer in the northern hemisphere. There's more light that falls on the northern hemisphere, and temperatures tend to be hotter than in the wintertime. Conversely, when the Earth's axis at the northern hemisphere is tilted away from the sun, wintertime will be experienced, and the temperatures will tend to be colder than in the summer. Again, this cycle is controlled primarily by the tilt of the Earth's axis, and that tilt will change as the Earth rotates around the sun. The third cycle that affects Earth's temperature is called the Milankovitch cycle. This cycle is caused by 3 changes in Earth's orbit around the sun. This cycle will tend to repeat itself approximately once every 100,000 years. Accordingly, there are 100,000 annual temperature cycles on top of each 100,000-year cycle displayed in this chart. On the graph here, you can see that there's a warm point, which we call an interglacial, and today's Earth temperature is represented by this change in color line. Interglacials are the warm periods in this cycle, but these cycles are not like the daily or yearly cycles. These are not linear. There's a period of very steep cooling, more gradual cooling, but again, very rapid warming. And I want to point out that we're currently here in this chart, and we're going back 100, 200, 300, 400,000 years. If we look at where we are today, you will see that Earth's current temperature, which is basically 57 degrees Fahrenheit, is cooler than it was during the previous 3 out of the 4 interglacial periods. And that's what these periods are called, interglacial periods. Specifically, it was much warmer during the previous interglacial than today, about 5 degrees Fahrenheit. And that was also the case during the 3rd and 4th previous interglacials. Now, the variations in this chart are primarily induced by the amount of sunlight that falls on the northern hemisphere, especially at around 65 degrees north latitude. This graph depicts the amount of sunlight hitting the Earth's northern latitudes at 65 degrees north in mid-July, from a period of time from the present on the right all the way back to about 1 million years ago on the left. As you can see, there are a lot of deviations in the frequency and magnitudes of the peaks and valleys in this chart. These changes are due to the interaction of 3 aspects of Earth's orbit as it rotates around the sun. This first one of these is called eccentricity. It basically is a factor relating to the circular or non-circular basis of the orbit of the Earth around the sun. This changes over time, and sometimes the orbit is more circular, and other times it becomes more elliptical. As you can see here, when it's more elliptical, the Earth is further from the sun during summertime and closer to the sun during winter. When it's more circular, like here, the difference between summer and winter distances between the Earth and the sun are not nearly as dramatic. So it's more even with a circular orbit and more uneven with a more elliptical shape to the orbit. I'll mention that the changes in the elliptical shape of the Earth's orbit follows a approximately 100,000-year cycle. Another factor that plays into the Milankovitch cycle is called obliquity. It's the tilt of the Earth's axis. The change is not very dramatic, but even at a small change, it has a big effect on the amount of sunlight falling on the Earth's northern latitude. And the northern latitude is important because there's more land in the northern hemisphere. And when there's more sunlight in the northern latitudes, the Earth will tend to warm up a lot more than when there's less. So when the tilt of the Earth is greater, like it is right about here, that's about the most it gets. When it's greater, most of the warming is up here. When it's at the least, it tends to be cooler up here. The changes in Earth's obliquity follows a cycle that averages approximately 41,000 years. The third item that affects the Milankovitch cycle is called precession. It basically is a wobble in the rotation axis of the Earth. It tends to move around, and this cycle changes, as you can see, the amount of sunlight that would hit the northern hemisphere. The precession cycle operates over approximately 21,000 years. Now, because the three cycles operate over different time periods, that's why we get these ups and downs over different periods of time in different amounts. In the graph here, that shows the amount of sunlight falling at 65 degrees north latitude in the northern hemisphere. Because the three factors that affect the Milankovitch cycles operate on different timelines, we get this very non-synchronized curve to the temperature changes. I'll point out that in the warmer periods, which are called interglacials, the Earth's temperature all around the world tends to be much hotter than during the colder periods, which are called glacial periods. And the cold periods could be much, much colder than we currently experience. Again, I'll point out that our current temperature here is about 57 degrees Fahrenheit. 125,000 years ago, during the previous interglacial temperature was a good 5 degrees or more warmer than present, and this was the case during the third and fourth previous interglacials. However, if you look at the cold periods, Earth got really cold during the dips. Here, we were looking at a temperature running around 10 degrees colder than today's average, and that held fairly consistent all the way through each one of these Milankovitch cycles. Now, if we look at the general shape of this chart, we'll see that there tends to be a very rapid warming of the Earth's temperature, followed by a slower, longer-lasting cooling. Rapid warming, slower, longer-lasting cooling. There's a lot of ambiguity here, so we'll skip that. Once again, very rapid warming, long drawn-out cooling, then up to the present, a very rapid warming. And if we look at the chart even in more detail, we'll see that the cooling trend was very steep for a small part of the time period, and then there was more gradual, very steep drop, more gradual, very steep drop, and then more gradual. Before moving on, I'll mention that the warming and warm periods of these 100,000-year Milankovitch cycles, the warm periods tend to run for about 20% or 20,000 years of the cycle. The cooling down portion cold periods tend to last about 80,000 years or 80% of the cycle. This chart shows a prediction of where temperature might go over the next several thousand years, and it kind of predicts that we're looking at the same general trend that we had since the last interglacial. That is to say, a drop from warm to cold, warm to cold. Or if we're going to compare the actual behavior during the previous cycle, we would be looking at a very steep drop in temperature and then a more gradual continuing drop-off. But again, we're probably going to get to that very cold period of time. Now, there is a contemporary concern that burning fossil fuels is actually increasing Earth's temperature. As we've seen, in the previous Milankovitch cycle, temperatures were going up and down, way before humans started burning any fossil fuels. Also, the peak periods here, the interglacials, tended to be relatively short, somewhere between 10 and 20,000 years in duration. The burning of fossil fuels has added to the carbon dioxide in the atmosphere. Carbon dioxide is a known greenhouse gas, and it can trap heat in Earth's atmosphere. It's now considered likely that the effect of adding carbon dioxide to the atmosphere by burning fossil fuels, that's called anthropogenic sources, has likely increased the length of time that we will experience this current interglacial period. It's likely that instead of this one only lasting maybe 10-15,000 years, it might last as long as 20 to 50,000 years. So basically, burning of fossil fuels has quite possibly bought mankind a longer period of time to experience life on a warmer, more accommodating Earth. But eventually, the next Milankovitch cycle is going to kick in and create a cooling event. And that cooling event is going to be accompanied by lots of glaciers in the northern hemisphere, and that will drive down the temperature of the Earth. So sooner or later, we are going to experience a next glacial period, and that will not be very accommodating to billions of people currently living on Earth.